Hey everyone, welcome back to my YouTube channel. This is Workshop Quick Takes. Today is part 2 in a 2-part mini-series we did as a 3rd anniversary special. Yes, July 2019 was the first ever video posted on this channel, and it involved a little miniature 12 volt, 13.8 volt bench power supplies that you can buy almost anywhere. We did that video for our now defunct tech website and decided that, hey, why not go back to our roots and do another power supply video, but this time let's do DIY and let's build it better. Specifically, this power supply. Now this doesn't actually exist yet, it's a figment of your imagination. You'll have to watch to the end of this episode to actually see it built, and then it'll be real. But the result speaks for itself. Turned out fairly compact, it's a little bit heavy because of the transformer we use, but it does what we need it to do and is very useful. Now today we're going to try and give you the highlights in as concise a manner as is practical considering the size of this project. There was over 7.5 hours of video footage that I had to comb through. That's from each camera. And likewise, there was probably another 7 to 8 hours that wasn't recorded at all, just a little miscellaneous wiring and other tasks and hardware store runs and all that kind of stuff done in between. But it is worth putting your hands to something and actually seeing an entire finished product rise out of it. So, without further ado, join us by stepping over to the workbench and let's get fabricating. Okay, next problem to solve here is this transformer that I pulled out of an old uninterruptible power supply has no mounting hardware. When it was installed in the UPS, the ABS plastic shell was molded such that it clamped it tight in there, and so they didn't make any other provisions. Let's try these pieces of scrap aluminum I've got from elsewhere. This is 1/16 by 3/4. It's not super thick, which I'm hoping means I can put some bends on it without breaking it apart. I might have to use a bit of heat to do that. Okay, next step. Got all the fronts, back, top piece off of this box, leaving just this. What I want to do is try and get a good mounting point for the transformer. Now, here's what I'm thinking. Right about here, I believe, is where I want the meter module. Over here is where I'll have the terminals. I'll probably bring the power in on this side over here along the fuse block. I don't know why, but for some reason, whenever I lay out a chassis, I always like to bring hot AC power in over on the back side here, and then kind of lay things out across this way. There's a screw coming here from where one of the bottom feet is mounted. But as long as I can get the wires out of the transformer, and conveniently they come straight up out of the back, which means I can kind of push this back all the way to the screw there. Something like that is probably going to give me a fairly good mounting position. If that looks good, and I think it does, let's go ahead and just hit those with a marker, and then pull this back up and off and see where everything fell. This stage of building any project can be pretty tedious because you're going to have to start putting things together and taking them apart again. I mean, that's true for any large project. You're probably going to pull things in and out a few times, maybe even completely install and uninstall some of the parts more than once in order to get everything where it needs to be. Now, the other thing you always want to watch out for when you do this is you may have avoided a screw from the top side, but did you completely avoid that from the bottom? In this case, you can see just by looking at it, yeah, we're way outside of that. There are a couple steps that are often skipped by novices and people that are in a hurry when it comes to drilling holes. The first one is center punching the hole you want to drill. The second one is stepping up from a real small bit to progressively larger bits until you get the hole you like. So there's another little task out of the way. We're on our way to getting this thing constructed. Okay, this is the back panel from the case over here. We know the transformer is going to be filling this area over here, so the next things we need to figure out is how to mount these. This is going to be the power inlet, and this is going to be the thermal protective breaker. That's going to go somewhere right about there with this nearby. There are a couple considerations. One of them is that this panel is very thin and flimsy compared to some chassis I've used, so I want to make sure I mount this as close as I reasonably can to the lower corner. That'll give it some extra structural rigidity when plugging and unplugging it. In any case, since the transformer comes right up to the halfway point, we know somewhere in the halfway point on this side is where we want to be, and if we're going to put this as close to the corner as possible, that shouldn't be an issue at all. So what I'm going to do is I'm going to take some of this yellow all weatherproof painter's tape, since it contrasts nicely with the blue, and just line the exact edge of the panel here. Okay, so that's going to mark off the area I absolutely have to avoid. Make sure that my lines line up, they do. Again, assuming that this is going to be the bottom corner. And I'm going to have an outlet here, and then this either over here, which is one possibility, or maybe just up here to kind of keep things compact this way. Next, I'm going to need some dimensions off this, and there's a few different ways I could do that. I could flip it over and try and trace it. This might actually work on this one. Okay, the next steps are going to take place on this drill press here, where we are going to drill 1/16 inch pilot holes in 1, 2, 3, 4, 5, 6 locations. And something to watch out for here that we've already started to do. In punching these, begun to deform the metal, warp it backwards a bit, so we don't want that to get carried away. Okay, to finish eating out this hole, I'm going to use something called a nibbling tool. I mean, you could saw it, you could do whatever, but this here is kind of a nifty little thing if you can get your hands on one. Just sit there and takes little bites out of the aluminum. Works extremely well on very thin material like this. You're like filing in there and that's it, because it already fits now. I don't have to worry about rotating it any at all because the screw holes still line up perfectly, so that's in good shape. And then just to prove it, fits perfectly still and no interference on the backside. Next thing is, where do I want this? Traditionally, it could go a couple different places. One of them is off to the side, and the other is up here. I'm probably going to need some space for wiring. I think it's going to make more sense for me to stack them. Okay, next exciting step, we need to lay out the front panel and get holes cut for that. Now I've already gone through this little guy. Probably the best spot for it is going to be somewhere right about here. That will leave space open over here for the 2 sets of output terminals, and then also, of course, a couple fuses or other protection devices mounted nearby. So we put this above, and we have a power switch below. So what do we do for a power switch? Well, if you have access to eBay or a surplus store or a stash of parts somewhere, then you do have a few options. Just looking at what we got here, some of these switches are lighted. I do kind of like those. You just need to make sure that they are compatible with the AC power supply voltage that you are bringing in. There are, of course, various styles you can go with. Here's another example of a lighted switch in green. This is a surplus unit I probably won't use, even though I do kind of like the look of it, because when I switch it off, it balks a little bit. So that's got some wear and tear on it that I'm not going to accept. This one here is a lighted switch, and if you look at it closely, you might recognize it is probably off of a fairly old Weller soldering iron, but I'm not quite sure that's what I want, because the module here actually does have a backlight come on when you switch it on, so assuming everything's working correctly, you're going to get a lot of visual indication that this thing is switched on. So I'm looking at maybe something like this, or this, or this, or even this if you want something tiny, or this if you want something gigantic. I do like the look of these two. Both of them have the universal IEC style on-off symbols on them, and I don't know, I think that kind of looks pretty good. It has a nice round hole with a thing on here, so I don't have to use the nibbling tool if I mount this one. I just have to drill that out with a stepper bit. You know, other options, nothing wrong with these. But I'm looking at these thinking these both look good, and I kind of like the look of that one right there. It's just got the right combination of size, width, and height to really just fill out the front of this panel. It's not too small, it's not too big, it'll do the trick, and it's clearly visible what it's doing. So. Okay, for this next step, we need to get our rectifier circuit set up. Now, that can be pretty simple at its most basic level, a couple diodes and a capacitor, but we're going to do just a little bit better than that. Note the part number there, GBPC3504. That part number on a rectifier corresponds to 35 amp, 400 volt. I don't know if it's actually that because, again, I think I might have gotten this off of eBay Gray Market or something like that, so it's possible that it's a lesser model that was counterfeited. But since we only need a few amps, whatever reserve capacity it does have will be more than enough, especially once we mount this on a heatsink. Okay, so that's what this plate's going to be. If I mount this upright in the kit chassis to save a little space, this should mount nicely right about there. And then on the back side, I can have my capacitors and a couple terminal blocks and whatever else on a circuit board that mounts like this. And then the screw holes for the standoffs on this will go around the corners. This will have its screw coming out in the middle somewhere-ish. And there's one more thing I do want to put on here. I'm going to put a transformer secondary fuse in line with the input to one of the leads to the rectifier. Reason for doing that is that if the rectifier ever does fail, it can go to a fairly low impedance short circuit condition. And, you know, with small power diodes, usually you'll just end up blowing these up. But with these cases and their heat sinking properties, it might actually sustain that fault for a while, long enough to burn out the transformer winding. So if you put a fuse on one of the secondary leads before you go into it, or if you're doing a center tap transformer on both leads, then that will help protect the transformer winding against a rectifier fault. Doesn't happen that often, but can. And the other thing I need to think about is I'm going to put a couple screw holes in here so that this can mount vertically in the chassis, but unfortunately I didn't leave a lot of base plate here, so if I do that, it's not going to be very stable. So I'm thinking down the center, on the back side of the rectifier where I have a screw coming through anyway, I might just mount this brace bar and then cut and fold it so that I can add another screw on the back side of the chassis. And if I install a riv nut in this and then screw it in through the back of the chassis, it'll add another point of structural integrity. One other thing I'm toying with here, the back side of this regulator has this heat sink, but there's two problems with it. One, it's passively cooled, so I don't know if it can actually sustain full output without having to go into a thermal shutdown. And second of all, the fins are the wrong direction. Anytime you have a heat sink that's going to be purely passive, you want the fins in line with the direction of airflow so the air convects up through it. Now, if you add a fan, that's no longer applies. The fan will blow air through and cause the actual convection effects. So I'm thinking about using something like this. Unfortunately, this here's a little wide. I don't think I can mount it straight on the fins, but maybe if I turn it slightly. Note that if I just put a fan on this and start blowing air out of this, it's going to blow hot air across these electrolytic capacitors. And yes, that is a common failure point. You open up older equipment that has failed due to failed capacitors, and quite often you'll find that one way or another, there's a capacitor in line with heat flow from a heat sink. So I don't want to just blow air over them. So what I might do instead is flip this around so that it sucks air through this way, cools the entire back side of this, and then brings the air back. But for that, since I'll have a 24 volt source and a 12 volt microfan, I'm probably going to try and introduce this buck regulator. Now, about this circuit board layout here. I've got an option. I'm going to try and use 2 capacitors, and these here I can either mount to this way, or I can mount to this way and take up most of the board space that way. And I think this way works better, because then I've got space here to put a couple of these screw terminal blocks that I'll use for output wiring, and maybe I'll also still have a place left to kind of just tack this on the corner of the board somewhere. All right, let's do it this way. I'm not going to sketch out all the schematic parts that we covered in detail last time, so suffice to say, we have our power transformer here. On this side, we're going to get somewhere around 18 volts AC. We are then going to connect onto the one side of our rectifier board where we have the transformer secondary fuse, which is probably going to be somewhere in the area of 8 amps. And we will have our bridge rectifier, which instead of drawing out, again, I'm just going to draw as a square with 2 AC terminals, a positive and a negative. So on this side of it, our positive and negative output is going to be around 24 volts DC. But if you watch our first video, remember that until we do something else with this, the waveform that started as an AC waveform on this side is just going to look like this coming out here. So the output of here is going to go into a terminal block on our little circuit board that we're going to build. From the circuit board, we are coming out and we will have a pair of capacitors. These are big electrolytic capacitors capable of storing a large amount of energy. And although I didn't show it on the original drawing, I am probably going to throw in a little ceramic capacitor like this here. And that's going to be something like 100 nanofarads maybe. And that is not a polarized unit, it is simply there to help shunt high frequency harmonics from positive to negative. But then these two we have at 4700 microfarads, maximum of 50 volts times 2. So we have our 2 polarized electrolytic capacitors. Remember, capacitors in parallel sum their values. If it's resistors in series sum their values. Coming off of here then, we're going to have 2 things going on. The first is we're going to give ourselves 2 positive output terminals and 2 negative output terminals. So plus plus and minus minus. One set here is going to go to our power supply module. The second pair, for now, is going to be a direct output at 24 volts DC, more or less. And we'll probably end up adding a fuse in here somewhere. At this point here, we're going to put in a little tap. We're going to get our little buck converter going. And so this is going to be a DC to DC supply. So we have our positive and negative in, and then we'll just say we have our positive and negative out, which in turn are going to connect to our fan. There. Now in my collection I do have a spool of tinned copper bus wire, but unfortunately it is not in this workshop. So what I'm going to do is I'm going to take some 14, I think this is, solid core copper mains wire, and I'm just going to strip off insulation and get myself some pieces of bus wire. Works well enough. Something to think about though when doing bus wire soldering, because I've encountered it before, I know it can happen, is if you get a nice piece of wire going and then you solder, well, you're heating this up to 650, 700, 750 degrees Fahrenheit, and then it cools back down to room temperature. Well, guess what? Metal expands and contracts. So if you get too aggressive tacking this down on the board at every single pad, you're going to find out that it's going to pull tight when it cools down and actually warp the board. Okay, now that we've got that paint on there, let's just trace out our paths real quick. We have the negative bus on the back side here coming around to these two, so I'm going to paint these, or mark these two black and mark those two red. And those will be our 2 positive and our 2 negative outputs. Next up, I need to figure out how to mount this and also wire it off the board here. Keeping in mind also that I need to bring in a pair of leads that are going to be coming around the back side of this and connecting to a rectifier over here. Okay, here's a step every hobbyist would prefer to skip, but let's not. Before we go any further, gluing this capacitors down or otherwise assembling all this, let's test this sub-assembly, make sure it works, and let's do so by starting at very low voltage and then ramping up. We'll figure out, first of all, are we getting the voltage we expect out of here, and then we'll look at the voltage coming out of here for the fan and try and tweak it a bit, because I don't want a full 12 volts on that fan. I want to dial it down to maybe about 10 or so. That should be more than enough to start it up, but it will allow the fan to run a little slower and a little quieter. Okay, so let's start by turning on the plus 25 output. We were at 0.02 volts according to that. 0.02 volts. That's a very nice low voltage that won't blow up our capacitors, and it also will resist a very high inrush into those capacitors, because that's a pretty healthy bank. I mean, 4,700 microfarads twice. There's a good place to clamp on a negative. There's a good place to clamp on a positive. So actually turning that back on. 1 volt. 2 volts, 3 volts. Let's confirm that again on here. Yep. Now we should just barely be at the turn-on point for our regulator here. Now we're getting nothing out of it at the moment. There we go. Okay, so reading positive voltage out of the regulator. That's a good sign. Means we connected everything correctly. 12 volts DC, 0.09 amps. So, I'll put on. Little fans like this normally have a pair of arrows. One of them says that way, meaning that's the direction of rotation. The other says that way, meaning the direction of flow. Working as expected. Let's try turning this down slightly. Still moving here at 7.5 volts. The question is, will it start at 7.5 volts? Only one way to find out. Oh, it actually will. So we can actually run that somewhere right around 8 volts. Still get plenty of air and enough air to make a difference and no noise. I like that. Okay, now that it's working, we're ready to start assembling everything. So let's go ahead and commit to glue on this and give it time to cure while doing some other tasks. If you've never seen this before, it's a DAP Quick Seal. It's an adhesive caulk, so it acts both like a kind of a glue and a caulk. It's not quite the same stuff that I think they use commercially. This here is kind of a vinyl caulk, so I'm not sure it would meet a UL listing for flammability or any of that kind of stuff, but for a project like this, it's more than fine. Okay, next up, we need to get the bridge rectifier on here, and since we do have a few things protruding, we need to make sure that whatever we do with this doesn't protrude on the back side, and towards that end, I'm going to use either this screw, which has a very thin head on it, or I could even go countersunk if I have to. Same thing for the fuse block over here. I've got to come up with a solution on that as well. If this is going to be facing like that, and I mount this thereabouts, or with the standoffs, I think we'll be okay. So let's go ahead and just get these laid out. This needs to be fairly high up on here because I've got to have room for the fuse block down here. Need to be high enough up that I can still get to like a lock nut or something down here that'll hold this in place. So I just need a screw hole that's centered right about there. Let's go ahead and measure that off just to make sure it came out. But I think the old eyeballs did a decent job. Just over 2 1/8, and I'm at 1 1/16. Oh, that's perfect. Same thing for the fuse mount, right about there. So one more round of metal work on this. A couple more holes to drill in the chassis, but we're getting close. Okay, the task of grounding this chassis is proving a little bit interesting. I've had to work through a couple ideas, and I think I've come up with something now. First off, I'm going to ground the base piece to the bar using a jumper exactly like the one that I've got up in there. One thing I did have to do, which I've done over here also, was take a chisel and grind the extra powder coating out of that hole to make sure this screw makes a solid connection. But to prove that it does. Good. The reason this is important, two reasons actually. One is for short circuits. If a 120 volt wire gets loose in here and touches a metal piece somewhere, you don't want that metal piece to be isolated from the ground, which is coming in on the socket back here. And I'll also make a nice big fat star on one of the transformer legs, because the transformer is the largest potential source of fault current. In fact, if you get a fault in the primary winding of the transformer, it'll be pretty much like putting a pair of keys or a screwdriver or something right across the mains. So what I'm going to try and do over here is I've got this, well, I've got two pieces of material here. This one's actually a very, very thin piece of fiberglass with copper plated on either side. This here is an actual piece of copper strip, and I think that's what I'm going to end up using. But let's start with getting this other one over here done. And hopefully I can pin both of those in there with one crimp. So this is going to go from top to bottom. But then the other thing that I'm going to do here is bring a jumper down and screw it to the back of a tab that goes maybe, I don't know, like this, I guess. And then pinches over. This is going to get tedious. It's going to be some trial and error with making different pieces and connecting them together. But I mentioned the first reason for doing it was fault current. The second reason is for EMI, RFI blocking. There's not really any large switch mode power supplies in here, but in spite of that, a large rectifier diode operating under heavy current can actually generate a lot of ringing up into high frequency ranges. The filter on our plug will help keep some of that from going back out into the mains, but there is also some potential to radiate out of the chassis if it's not fully shielded. So by having all plates connected to the ground point, it'll help eliminate that issue should it become one. So we'll cut this off in a minute, come back and take a look at how it turns out. Okay, back again. Here's what we got. Okay, this is the back, this is the front. There's a bonus jumper that's been left up here to connect this metal piece to the base. On the back side here, we've gone top to bottom again and added a copper tab. And the way that's going to work is this plate will mount here, and I've knocked the powder coat off the aluminum so that when that's screwed down, that should make a nice ground connection right there on the corner. Likewise, on the front here, same thing again. Clean the corner and then put it over the screw hole with another copper tab there that's tied into that system. And once the screw's in, nice firm grounding connection. Finally, there's the issue of what to do about the top cover. I thought about maybe making some pressure tabs or something up here and kind of played around with that idea, decided it was more trouble than it's worth. So instead, I've added a screw right here and right here only, so you have to install it this way if you want to be able to put it back in. And that is going to have a very large steel screw going right there, bonding the two pieces together. So between all of those, every piece of this chassis should have a very nice solid ground path. What that means is we can now go to final equipment assembly and start the wiring. Alright, some basic assembly to start out with here. These we're going to need probably, for using English, number 440 screws, unless we want to drill these out and use 632, which I've also done before on outlets like this. And then we're going to need to get this installed, and we will need probably JB weld epoxy or something like that around the back side in order to seal in and keep these things from rotating freely. And then we've got a fuse holder, our banana terminals, our power supply module, and our power switch all need to be mounted on this one. And then we'll move on from there and install the parts and pieces that mount inside the chassis, including the transformer and the rectifier module. Okay, first up we gotta get this transformer mounted in here. I've got these bolts. I'm gonna go ahead and put 3 of them in right away, save the 4th one until we get a proper ground terminal made that's gonna come back to the outlet. Now because this base metal is so thin, I'm just gonna put these grade 8 washers I have on both sides of the connection. Next thing we need to be thinking about is getting a wire jumper on the back of this plate that connects the fuse to the line input on this outlet. Now, I typically have some trouble remembering which pin is line and which pin is neutral on an IEC power cable. For those of you in 240 volt countries using it, if you use a 2-pole disconnect, not a problem, but if you have line and neutral like we do here, then yeah, one side's definitely going to be polarized. And on the US, when the ground facing down is this one on the right, but it's always this pin is the line and this one is the neutral. You can look up the pinouts online all day long if you like, but frequently, if you've already got a power cord handy, it's easy just to do a continuity check. Wait, that didn't sound quite right. There we go. Okay. So it's this pin here, which conveniently corresponds to that there on the right. So if I'm looking at this as though I was about to plug into the wall, there's my hot. And I can go ahead and mark that on the side here just for reference with a little L for line. Okay, I've temporarily installed the front and rear panels. We're now at the stage where the entire AC system is assembled. I finished the wiring off camera because that gets a little tedious, but power comes in the IEC inlet. The line side is over here, neutral is over here. So on the line side, we come in, we have a little jumper that immediately goes to our protective device. This is a standard and proper way of connecting things. You always go through your protective fuse or circuit breaker before going through your power switch. So straight off of here, with this filtered IEC inlet, there's a jumper to this, and then this comes back out via the black wire over to the front panel switch. Output of the front panel switch is this blue wire, which comes around underneath here and ties into the transformer. Once we go through the primary of the transformer into black, brown is tied off on the primary because as a tap we're not using. White put to neutral, back to the outlet. So when I flip this on, I should be getting about 17 to 18 volts AC on these two terminals, and there's only one way to find out. Power's off at the moment. Plug that in. Volts AC, hit the 20 volt scale on the power switch and hope it doesn't blow up. And there you are, 16 volts. The AC side is working fine. We can continue assembling the DC side. Time to start the DC section of the chassis. I've now pulled the front and rear panels back off. A couple changes have occurred. I realized that it was going to make more sense for me to flip this from this way to this way, and so I bent this back and adjusted the position of this so that everything still fits neatly. I get better access for the conductors from the transformer. I still have my two screw holes back here, but originally those two screw holes were this and this. So by sliding that over, it's now this and this, and what I'm going to do is use this third screw hole that was already here to have a cross brace that goes to the front and holds the front and the back together, because otherwise they flop a little bit. This was constructed from just a piece of universal steel mounting bar for framing brace, and I put the same rivets in it again, so I got more of these 1024 screws that will go into those. But in any case, what I'm going to do next is get the two transformer leads here, the DC leads, plugged in here, and get this mounted on the base piece. The fuse I've gone with in here is 15 amps fast flow. That should be more than enough. This I think is at least a 500 VA transformer, if not 750. We had that discussion before. So if there's a short circuit in the bridge rectifier and we get a very low impedance, getting 30 amps through here to blow a 15 amp fuse, keep in mind fuses won't reliably fail till they see at least twice their nominal load current. But getting this thing to put a short circuit current of 30 amps through this fuse will easily be accomplished if this bridge rectifier fails, and so it won't burn up the transformer. So now, I could probably go back to like this for a minute. Off camera, I've wired up conductors for the fan drive. And I'm thinking, what I want to do with these is, I'm going to come through here with more of these nylon lock washers. So let's see how that works out for us. It looks like I've used my stock of nylon colored lock washers in 632, and since the hardware store is already closed for the night, I'm just going to use regular nuts and lock washers. Okay, off camera, I've had this thing apart and back together and apart and back together probably 4 or 5 times now. Purpose of which is just to get everything test fitted and properly assembled. But now, we've got 2 components that we've previously tested independently, the AC section and this DC component here. And now it's time to find out if we plug this in and connect those together, we should still see around 24 volts here and around 10 volts. I think I had it set around the fan buck converter. So this one should get us 24, this one should get us somewhere around 10. And if that all checks out, we're finally ready to connect the front panel up. This tells me now that everything else is working, so we can start connecting the front panel anytime and get the output we're looking for. Moment of truth time. Everything is hooked up. I should be able to flip this on. I should see this light up. I should hear that fan spool up. I should get about 24 volts DC on here, and this I'm expecting to come on at whatever that was last set at. So let's find out. Yeah, there we go. 22.5, 23, 24 volts. So it's as close as it gets. And we're operating at just about a 11.95 volts over here. And that agrees. 22.39 volts in. So far, so good. Hey everyone, thanks for joining me on another episode of Workshop Quick Takes. Kind of wrapping up our 3-year anniversary by going back to where we started with power supplies, but here's a little epilogue. When we think about the cost of what it took to put that together, I mean, we're looking at $20 for the chassis and about $20 for the little meter thing, and then parts and pieces, you know, $20 here, $20 there. Pretty soon you're talking about real money. Well, historically, I mean, that was a great way to save money, especially if you get parts as found objects or scrap, like for example, the transformer we used. But these days, if you just want the functionality, DIY is not going to save you anything. DIY is solely about the experience. It's about having the fun of actually doing it. This arrived a few days ago from eBay. Paid about 60 bucks. Let's see what's in it. Oh look, DC power supply user's manual. Here we have a cheaply put together, but nonetheless purportedly functional lab bench DC power supply. It's got current control, it's got voltage control, Power on, power off. Very lightweight. Everything in here is done with switching electronics. Fan on the back side already. But output 0 to 30 volts is 0 to 5 amps. $60. Does everything that the power supply we put together did. Costs less, weighs less. Almost the same size functionally. So we'll put it on the bench for a minute, take a look at it before we go, and see if it actually does what it says it does. That's the stuff. .8, 16.72 on the Harbor Freight meter, we're there. Go back to our old friend, the high current automotive light bulb. 12.1 is close enough. Wow, I didn't like that at all. That tripped the ground fault. Interesting. So maybe the $60 wasn't so worthwhile after all. Protection, short circuit, overload, over voltage, over temperature. Supposedly 0 to 10 amps, but that's clearly not going to happen. Surprisingly complicated. I mean, I don't know the quality of the components, but that is a decent looking power supply in there. It's not assembled very well. You can tell by how some of this stuff is just kind of pushed over to the side, but all the parts and pieces are there to do what it claims to do. Okay, let's try that again. Turn it back on. It looks like it remembered and rebooted to the location we were attempting. Huh. And it still trips the ground fault outlet. So something sounds like it's arcing in there. I'm gonna have to return this one. And there you go. That's a lesson on what happens when you buy a cheap power supply off eBay. May work, may not. Well, that was a genuine surprise. I really thought that thing would work. I mean, they sell a ton of those on eBay from all kinds of different manufacturers, so most of them must. But there again, that kind of takes us full circle to our original power supply video. That's the risk when you order direct import kit off eBay. Sometimes it works and sometimes it doesn't. So we'll have to return that one. Probably won't order another one. Didn't really need it. Just wanted to try and use it for this video. And since it's not going to do anything for us, I don't want to take the chance twice. But in any case, it is an option out there if you're willing to take the chance of returning one or two. It's going to be cheaper than DIY, but the DIY is going to be a lot better built and longer lasting. So wherever your hobbies take you, we hope to see you there, and we'll see you again here next time, whenever that is. Has anyone seen my phone?